Hi, so today we will be formulating the Euclids algorithm for calculating the GCD of two numbers. I want to convince you that you came up with the algorithm yourself. So essentially, if we are finding the GCD between two numbers, say a and b, we could stop and think, what does the greatest common divisor mean? It means that we are looking for a number such that for a and b, their largest number r, such that a can be written as some unique factor a1 and common factor r, and r is also a common factor in b, such that b is equal to b1. So the main idea behind Euclid's algorithm is even more simple than the algorithm itself. Knowing that r is common in both a and b, it is interesting that r is also a common factor between a and a plus b, since a plus b can be written as r into a1 plus b1. So this means that the GCD between a and b is equal to the GCD between a and a plus b. Let's try this with real numbers. So say 17 and 4. So the GCD between 17 and 4 is the same as the GCD between 17 plus 4. 21 and 17. As interesting as this fact is in computation terms, we have just made the work of computing the GCD even more difficult than it already was. So now let's try something different, but based on the same logic. Since r is the common factor, notice that a minus b can also be written as a factor of r. So the GCD between a and b is the same as the GCD between a and a minus b. Back to real numbers. So say you want to find the GCD between 21 and 17, then this is the same as doing the GCD of 17 and 21. 17 equals to 4. And now we are getting somewhere, because the numbers we are getting the GCD of are smaller, it has become easier part. When God gives you lemon and you squeeze and get lemonade, you don't stop squeezing till we get every last drop. And so we don't stop there, we redo our victory to another level. So the GCD between 17 and 4 is the same as the GCD between 13 and 4. And not stopping there, it is the same as GCD between 9 and 4, and the same between 9 and 4, and the same as the GCD between 5 and 4. At this point, we can compute the GCD ourselves easily, but what would happen if we continue pushing on? So first of the GCD between the 21 and 17 seems kind of hard to think about, but the GCD between 5 and 4 is a lot more easier. And so if we continue, we find that the GCD between 5 and 4 is the same as the GCD between 4 and 1. And we know that the GCD, say that we are looking for the largest integer that can divide both number, in this case, 4 and 1, without leaving a remainder. If it is not obvious, this is 1. Since GCD between any number a and 1 is going to be 1. I hope you are brave enough to grab some pen and paper to see that yourself, if you don't believe me. As efficient as this algorithm is, imagine we can make it more efficient. So I hope you are familiar with the addition and its relationship with multiplication. That multiplication is just repeated addition. And so 2 times a is like saying a plus a. And 7 times a is equal to a plus a 5 more times. And so if multiplication is repeated addition, then this means that division is repeated subtraction. So if 7a divided by 7 is like saying subtract 7a times, and the remainder is what remains after the last subtraction. In this case, since 7 is a factor, nothing remains. But say it is 11 divided by 3, then it is going to be subtract 3 for 11 3 times, and remainder of 2, which is less than 3. And so we cannot continue subtracting. So if we look back at our table, then we can see that we are effectively subtracting from 21, 4 a couple of times, 5 times to be specific. So we can just say that since we continued with what remained, we can just do division just to get the remainder and deal with the remainder for a calculation as quote. We have seen the remainder is like what remains after the final subtraction. So we can say that we subtract the value 4 from 21, 5 times, and on the last time we cannot do a full subtraction, because what remained is 1 and 1 is less than 5. This is like saying, we divide from the value 21, 4 to get 5 and a remainder of 1. However, for our initial algorithm, we only interested with the remainder 1, and not answer we usually looking for when we do division the 5. Just a quick fact, this type of arithmetic that only deals with the remainder is called modular arithmetic. In the improved algorithm, now instead of doing repeated subtraction, we do division and move on to the next step with the divider and the remainder. This is because if we divide two numbers, a divided by b, which equals to some value c and has a remainder of k, where k is less than b, the GCD between a and b is the same GCD between b and k. This is the main idea behind the algorithm. And this saves as the repeated subtraction close, since we know that if we get that k, cannot be subtracted anymore by b without becoming a negative number. And the pair b and k is way smaller than that between a and b. This makes b and k easier to work with. Just to make it even more clear, the whole idea is based off the fact the GCD of small numbers is easier to compute than that between large numbers. So putting our original table aside a little while, we do another one that is based on division to reduce the size of the numbers instead of recursive subtraction. GCD between 21 and 4 is the same as the GCD between 4 and the remainder from 21 divided by 4, which is 1. No, look, it is easier to compute the GCD between 4 and 1 rather than 21 and 4. But the thing with Euclids, it never computes the GCD, even if it is reduced. A and B are easier to work with. The algorithm just gives a single answer. How? It does it by upgrading from repeated subtraction to repeated division till we get a remainder of 0. And this makes the GCD the divisor b. So here we would get 4 divided by 1, where 1 divides it perfectly with a remainder of 0. And in the next step, we find GCD of 1 and 0. The GCD of any two numbers a and 0 is always going to be a. So try for a quick example. The GCD between 12 and 3 is the same as GCD between 3 and remainder from 12 divided by 3, which is 0. And so the GCD is 3. Try with any numbers your head can think of. There you have it. You rediscovered the Euclids algorithm for computing the GCD. Have a nice day.